Okay guys, so we've just looked at Hess's law, which has said that the enthalpy from any reaction can be calculated from the enthalpies of other reactions as long as the beginning and the end states are the same, okay? So here, what we're going to talk about is we're going to have a standard path that we can calculate enthalpies for, okay? And this is called the enthalpy of formation. So what we're doing is, we're agreeing as chemists, we're going to have an energy that's measured for every kind of compound that we know of, and we're going to measure the energy that it takes to make that from its standard state, in inverted commas there, which we'll define, okay? Because there are so many reactions, scientists have created a table of enthalpies of making compounds from their component elements in their natural states. Okay, the standard enthalpy of formation, also known as the heat of formation, I use that term more, and more chemists probably use the term heat of formation more. The symbol for that is the enthalpy under standard conditions, which is that circle and line. Sometimes we abbreviate it to leave that out, but the lowercase f there, heat of formation, I'll use that kind of symbolism. It's the enthalpy of 1 mole of compound made from the elements, from the component elements in their standard state, how they're found at 25 degrees Celsius and 100 kilopascals, or how we find it in every day, okay, on Earth. So, for example, if we're talking about the heat of formation of sodium chloride, okay, so muggles know it as table salt, it's the enthalpy change for the reaction of taking the elements in their natural state. Well, it's made of sodium and chlorine. How do we find sodium in its natural state? Well, it's a metal, so we find it just as sodium solid. Okay, it's very reactive. We don't tend to trip over it on the sidewalk there, but just by itself, standard temperature and pressure, it's a solid, okay? Chlorine is found as Cl2, a diatomic gas, okay? And so they come together to form sodium chloride. So to form 1 mole of sodium chloride, I need 1 mole of sodium metal and half a mole of chlorine gas, okay? These are their forms at 25 degrees Celsius and 100 kilopascals. So when we're talking about the heat of formation of sodium chloride, we're talking about starting from sodium metal and half a mole of chlorine gas and making 1 mole of sodium chloride. And we can look this up in a table, and scientists agree that this energy is minus 411 kilojoules per mole, okay? So the heat of formation for any element is its natural form. Okay. Start again. The heat of formation of any element in its natural form doesn't take any energy to transfer it into its natural form. It's already there. So it's 0 kilojoules per mole. Okay? So it takes 0 energy to take an element in its natural form and transfer it into an element in its natural form. It's already there, okay? So if we're talking about the heat of formation of any of these elements, we're talking about 0 kilojoules per mole. So the heat of formation for iron as a solid is 0 kilojoules per mole, because that's how we find iron as a solid, okay? Manganese, also a metal, solid. If we find manganese solid and say, what's the heat of formation of this? It's 0 kilojoules per mole. O2 gas, the heat of formation of O2 gas. Well, O2 gas is how we find it under 25 degrees Celsius and 100 kilopascals, so its heat of formation is 0 kilojoules per mole. Same as chlorine gas too. Same as phosphorus, same as potassium, same as argon, same as H2, hydrogen gas. That's how we find it, okay? So any of those ones, it's 0 kilojoules per mole. For any others that are combinations of atoms, we look it up in a table, okay? So when we're solving problems now, we'll look it up in some type of table, or it will be given to you in a question. In an exam setting, it will be given to you in the question, okay? They're not on our data sheet, so when they're going to bring it up in an exam, they will give you the heat of formation values for any compound, okay? They won't give you the heat of formation of any of the elements in their natural state because because it's zero, and they're testing if you recognize that. So usually when they're doing heat of formation questions in any exams, they usually have a reaction with an element in its natural state just to test that you know that, hey, that's 0 kilojoules per mole, okay? One note here, be careful of the states of the heat of formation. The heat of formations of the same compound differ by the states, okay? Because you need energy to change between the states, okay? So be careful. Have I got an example here on the table of something that's repeated twice for each state? It's usually, I mean, the obvious I'm looking for is water here, but it looks like I've got all different. There'll be an example up later if I don't have it, okay? All right. Okay. How does this help? Well, the heat of formation values give us these two values. They give us a separate pathway that's standardized and is agreed upon by all scientists, and we've got tables for it, and we can easily look up these enthalpy values or heat of formation values, okay? So what we do is, remember our last enthalpies where we take our positives and add them together for the enthalpies. Here we find the difference between them, okay? And we'll soon see why in this graph, okay? So let me just erase what I've scribbled on, okay? So in this example, we've got some reactants going to some products here, okay? Now it's an exothermic in my example, but it doesn't need to be. They just differ, okay? And the difference is going to be the enthalpy. Just for this example, they're just a negative difference there, okay? So we're going to take the elements of all these in their natural states. And now the values down to here, that's just the heat of formation of the reactants. And the value down to here is the heat of formation of the products, okay? So the enthalpy of the reaction is going to be the difference between these two. Another way to think of it is, okay, if we're going on, let me get my pencil, I might change colour. If we're going on this pink pathway down to there, what we've got to do is see how instead of we're going upways, okay, and here we're going downways, what we're taking is this value going upways is just the negative heat of formation of the reactants, okay? So to get up there, we've got to put the opposite energy of the heat of formation in there. We've got to do the opposite. And here, going back down, we've got to do the positive, or just the normal heat of formation of the products, okay? So we're taking the positive of that and the negative of that, and we're adding them together. Or we could say that the enthalpy of the reaction equals the heat of formation of the products minus the heat of formation of the reactants, okay? So you can think of it as the difference, or you can think about, oh, I need to go up, so that's against the heat of formation, and here is with the heat of formation. Okay, so the heat of formation of the products with a positive minus the reactants is going to give you the enthalpy value for the reaction. Okay, let's do an example. So what is the heat of formation? What is the enthalpy for the reaction of, we've got C2H4, that's ethene, but we'll get to that later, and hydrogen chloride gas going to chloroethene. Okay, we'll get to naming that later. You just recognize the formulas. Okay, given that, the question's giving you the heat of formation of these. Okay, we've got a balanced reaction there too. So I've drawn it in here in tabular form to help you out. Okay. What have I done here? All right. Okay. So the heat of formation for the reactants is the heat of formation for the ethene, which is positive 55. I've written 55, but it's 52. And minus negative 92. So it's 37 kilojoules per mole to go down that way. So it's positive 37 to go that way. Okay. And then down here is the heat of formation of the products. Well, we've just got the one product, and that is the negative 112 kilojoules per mole, okay? So adding it on there. So you can do it that way, and you can see that, the difference between the two. But let's do it this way, okay? So the heat the enthalpy of the reaction is going to equal the sum of the heat of formation of the products minus the sum of the heat of formation of the reactants. Okay, so it's going to be, what of our products is going to be the heat of formation. I'm going to do square brackets. So our product is, there's just one of them, C2H5Cl. And there's only one stoichiometric mole out there, so we just multiply it by 1. And minus, big brackets, the heat of formation of the reactants. Well, we've got 1 mole of ethene, so the heat of formation of ethene. C2H4, sorry, I should say. You guys don't know what ethane is. And we've got 1 mole of HCl, 1 stoichiometry. So that's the heat of formation of HCl gas. Okay, put my values in. I get the products, negative 112, minus the reactants, so 1 times C2H4, which is positive 52 kilojoules per mole, plus the HCl is negative 92 kilojoules per mole. Put them in your calculator, and so we've got negative 112 minus positive 52, okay, so it's minus 52, and minus negative 92 is plus 92. So I get negative 72 kilojoules per mole for the enthalpy of that reaction. Okay, let's do another one here. What is the enthalpy for the dissolution of potassium sulfate, given that we've got the heat of formation for potassium plus and the heat of formation of sulfate and the heat of formation of potassium sulfate? Okay, so let's do the dissolution equation. K2SO4 solid going to, we're going to form 2 K pluses and 1 sulfate ion. Okay, make sure that you can balance that. Okay, so the heat, or what am I doing the sum of? I'm just going to do the enthalpy for the dissolution reaction is going to equal the sum of the heat of formation of the products minus the sum of the, I forgot the H. I'm doing terrible here. I'm gonna, okay, sum delta H subscript F. Let's fix this one up. So the sum of the enthalpies of formation, or the heat of formation of the reactants. That makes me feel better. Okay, so big bracket, what are the products? We've got 2 potassiums. So 2 times the heat of formation of potassium. And we've got 1 sulfate, so 1 times the heat of formation for sulfate. Minus the reactants. Well, we've just got the 1 reactant, so we've just got the heat of formation for potassium sulfate. Okay, so we've got 2 times, what's the heat of formation of potassium? Negative 283. Okay, and add on the heat of formation of 1 of the sulfates, so plus minus 909. And sorry, minus in between there, and minus the negative 1438 kilojoules per mole. Okay, so I've got 2 times negative 283 plus minus, so minus 909, and then I've got minus negative, so I've got plus 1438. I get negative 37 kilojoules per mole. Alright, so that dissolution reaction is just slightly exothermic. A little bit of energy given out. Have we got another example? I've got some examples from the textbook, so you can work through those in your own time and check them out. And I'll leave it there.